Hey guys, welcome back to Explore Electronics. Let us understand the concepts of Advanced VLSI, and here in this subject, let us move on to module 3 now, that is having verification guidelines and data types. The first half of the module covers how the verification will be and what are all the guidelines we are going to follow and how the things will be in verification. And the second half give us the details or depth of the data types available in System Verilog. So prior to that, module 1, module 2 covers the introduction to ASICs and how the data path designs are going to be done. And in the second module, we will be understanding floor planning and placement and routing concepts. So with this first module and second module knowledge, how the verification of that ASIC will be done will be covered in module 3 and module 4 and module 5. Let us jump on to module 3. The very first topic is verification process. What is the main verification process we are going to do and how actually the verification engineer job will be and what is the goal of the verification is the primary question here. So what is the goal of the verification then? It is only finding the bugs? No, if you say finding the bugs, it is partially correct. More of finding the bugs, we will be ensuring the correctness of the design and the designer has written the code and how much code and all the conditions we have verified properly to ensure all the functionalities which are working fine. That is the primary goal of the verification engineer. So before that, we need to understand the goal of the hardware design engineer also, and then let us move on to the goal of verification engineer. If you see a hardware design engineer, let us assume like a ASIC engineer, he is going to create the device that performs particular task. ASIC in the sense it is application specific integrated circuit, means they are going to design for a particular task based on what design specification. It means they will be having a specification document. With respect to that specifications, they are going to write the design that performs a particular task. So example designs can be a memory device, IC which supports memory read-write transactions with particular size, and DVD player, it has to play the video and as well as the audio, and network router, it will be capable of routing the things to a different devices, or radar signal processor, it will process the signals coming into the system. So these are a kind of ASIC examples, and this is the goal of the hardware design engineer. He has to get the design specification. Depending on that, he will be writing the design or is making the design which will be for the particular task. So if you look at the flow, how actually it will be means, first there will be a set of specifications. Depending on the specifications, or we call it as the requirements, the architecture design will be made. This architecture design in the sense how the system architecture will be. These are all the functions we have, and depending on these two, RTL design will be written. This RTL design will be a Verilog or System Verilog design code, and once the design is ready, it will come to a verification stage where RTL verification engineer has to verify all the functionalities in the design are correct. And here also we will be finding the bugs present in the design. More of that, we will be verifying the design correctness, right? After the verification stage is completed, this design will be given to the synthesis, and synthesis output will be the netlist. So this is the general flow how actually the ASIC design and verification works. So now we need to understand what is the goal of a verification engineer then. After the design is completed, verification engineer has to make sure the device, or just we say design, can accomplish the task successfully. That is, design is an accurate representation of the specification what we set at the starting. And bugs are what you get when there is a discrepancy in the design, right? If you found a bug, you need to report back to the hardware design engineer to make it correct, right? When the behavior of the device, when used outside of its original purpose, it is not the verification engineer's scope to verify that. So we want to know the boundaries also. It means, suppose a memory device is our ASIC IC, we are verifying, and it has only 1024 locations. Suppose while verifying, if we are verifying the next location like 1025th location and we are getting an error over there, we are unable to fetch that, it is not our scope, right? Only we will be having 1024 locations of the memory. So we need to know the boundaries of the design also. What is the size of the memory? Until that we can write and read, right? It is a simple example I have given. So likewise, there are different conditions we need to look for, and what is the boundary and what is the capability of that design is. And then as a verification engineer, we are also going to read the hardware specification document first, and then only we will be understanding what actually the verification plan is. So after reading the hardware specification document, then create the verification plan. After creating the verification plan, then we need to follow the steps to build the tests, that is Testbench, showing the RTL core correctness, which is implementing those features, right? So the 3 steps we can say as: first step is to read the hardware specification, then create the verification plan, then we are going to build the tests which will be showing the correctness of the RTL code. So we say verification engineer not only do understand the design and its intent, but also you have to consider all the corner cases in the test cases. So all the corner cases in the sense, if the memory device is capable of storing 32-bit in each and every location, we need to write 8 bits also, we need to write 16-bit, 32-bit, and also 1 bit or any particular bit, and also we need to verify. So these are maybe the corner cases in a memory device like that. So we need to understand the tests which are going to exercise this RTL code completely and matches the exact output. So the next thing is testing at different levels. Testing at different levels means different levels of verification. So what are the different types of bugs are hidden in the design? We need to identify at different level. So the very first thing is, and the easiest one is at the block level. Block level in the sense, suppose in our design ALU is one block and bus transaction unit is another other block, and packet handler or the network switch is other block. We are going to verify these things individually, and these modules are going to be verified by a single person like that. So these things require some of the individual test cases to check only the ALU particular functionality, only the bus transaction functionality or the network switch functionality like that. And the next level is beyond the boundaries of each and every block. It means we have integrated this ALU with the bus and also to the network switch, something like that. So we need to verify across the boundaries also. So boundary between the blocks we need to verify. Here some interesting problems may arise, like 2 or more designers read the same description in a different interpretation, and the output of the ALU may be connected in a different fashion for bus transaction or to the network switch. Means if these two are designed by the different persons. So in such cases we need to take care of the boundaries, different blocks boundaries and integration phases into consideration over here. So here the verification engineer job is to find the disputed areas. Disputed areas means the two designers have designed these two separately and they have integrated, and there might be a chance of error over here while crossing the boundaries. Those cases we need to check it over here. And the third level is entire system test. So you might have heard about the SIG verification and also the SOC verification. SOC which will be containing multiple blocks inside. So SOC verification in the sense we will be verifying the complete functionality even after the integration of those. So in such cases the DUT will be considered as an entire system and subjected to be tested. And here the simulation performance is reduced, means we are checking parallelly the ALU as well as the network switch and also the processor and things like that. And here the tests should strive to have all blocks performing interesting activity concurrently. So concurrently these blocks are going to perform, and we need to verify all those in a entire system level testing. And with all this action, data alignment and timing bugs may occur over here. These timing violations and the data mismatch because of the timing we need to verify in the entire system level testing. And also we can move on to the system level verification. As I said, the SOC level verification. Here the challenges will be again higher compared to these three. And at the block level, you can show the individual cells flow through the blocks of an ATM router correctly. At the system level, you might have to consider what happens if there are streams of different priority in a ATM router again. Which cell should chosen next is not always obvious at the higher level. Why? Because all those are at the concurrent execution, right? That's why there is no concept of which block I need to test it next like that. And you may have to analyze the statistics from the thousands of cells to see the aggregate behavior of the result. So the basic idea is we can test in the block level and then crossing those boundaries with integration phase, and then entire system testing, and then the SOC level testing. And these are all the different levels and the challenges we will be having at different levels. Then comes the verification plan. Once the specification we have read, then we need to go for the verification plan. We need to write the verification plan. Accordingly, we need to write the test bench. So verification plan is derived from the hardware specification itself, and then it contains a description of what features need to be tested, or exercise means what features included in the design need to be tested, and what techniques we need to use to put a stimulus logic, right? This is what we are going to consider while writing the verification plan. And these steps may include directed or random testing. Remember, directed testing in the sense we will be giving the data manually, and random testing in the sense we are randomizing the data what we are going to generate from the test bench. It may also contain assertions in the sense some checkers, hardware software co-verification things if it is there in the design, and emulation, formal proofs, and the use of verification IP. These are the different steps may be involved in the verification plan. Then comes basic test bench functionality. What is the basic functionality of a test bench we are going to write to verify the DUT? So we can say what is the purpose of the test bench. The main purpose, as we said, to check the correctness of the DUT, where we will be following these steps. First, we need to generate the stimulus that will go to DUT and apply that stimulus to the DUT. So applying stimulus to the DUT will be with respect to how the DUT is going to take the data one after the other. And then after DUT is going to perform its operation, we need to capture the response in the test bench only. So the test bench functionality is to generate the stimulus, then drive the data to DUT and capture the response back in the test bench. And we need to check for the correctness. We need to have a golden DUT in our test bench or golden reference values. With respect to that, the output of the DUT need to be compared and checked for the correctness. You can see here golden reference values. And then we need to measure the progress against the overall verification goals what we set at the plan level. So whether the goals are met or any other kind of verification we need to do to achieve those goals. So here some steps are accomplished automatically inside the test bench, and while others are manually determined by the verification engineer. And the methodology you choose determines how the preceding steps are going to be carried out. Why? Because generally in your level you might have written a Verilog test bench. The next level is the system Verilog test bench we are going to write. That will automate some of the process and it will make easy to generate the stimulus. And the next level is the methodology what we are talking about here, that is universal verification methodology. So that methodology gives us more flexibility to generate the stimulus and keeping a hold on our stimulus generation. So that's why that methodology what we adopted will be determining what are all the steps we need to carry out manually and what are all the steps carried by the test bench by its own in the tool. Then we need to understand the directed testing. Directed testing is a old approach we can say, or the traditional approach. We can easily compare this with the Verilog test bench what we are going to write. What happens in the Verilog test bench means directly we will be instantiating our DUT and then start giving the values by manually writing them as a values, right? That is a directed testing approach. Here understand the hardware specification and write a verification plan first. Here also the same steps, and each and every test concentrated on set of related features. Suppose if it is a multiplexer kind of design we are testing, we will be having a case statement inside the design which will be checking for each and every cases of the select lines, right? So to check those in the test bench, we need to give all the possible select lines as input and also a input data. So like that, we need to concentrate on set of related features, input and the select lines, how actually we need to give. In the test bench plan or the test plan, we need to write the stimulus vectors that will exercise these features of the DUT. It means 4 select lines are there in your mux, means all those 4 select line values we need to give. So those becomes the stimulus vectors, we can say. And then simulate the DUT with those vectors, and manually we need to review the results using log files. There is no comparator here in the test bench. There is no way to check the results of the DUT automatically. So this direct testing is writing a verification plan, then we will be setting some features related to the test, and then we will be driving that to the DUT, and the results we are checking with respect to waveforms and using the log files, right? And once that works properly, then we need to go for the next test what we are going to give. And here each test is targeted at a specific set of design elements. So I said mux example again. Suppose if we are checking only the select line with 0, 0 as a first test case, then we will be checking the second select line, something like that. Or if it is a ALU, we are verifying only the additional functionality first, then we will be checking only the multiplexing functionality or logical functionality and division, like that. So here the disadvantage is that you can see this coverage 100% in the sense all the functionality of the design is covered, means coverage is 100%, and the time required for that is, again, it is more. Why? Because each and every test we need to do, and then we need to go for the next test. That's why you can see it as a ladder. After one test is done, 10% coverage will be done. After the second level of test is done, 20%. Likewise, if you take again a concept of a ALU, addition, subtraction, multiplication, logical and or modulus, all those are become individual test cases, and completing those taking much time. So the disadvantage is that when design becomes more complex, it takes twice as long as to complete and requires twice many people to implement it. So that is the disadvantage is in direct testing. And what is the solution for that? Means you need to have a methodology that finds the bugs faster in order to reach the goal 100% coverage. That let us see in the next concept, that is methodology basics. What are all the disadvantages are here? Means we need to give the stimulus by our own. Manually we need to give the values. There is no random value generator here, and also there is no checker here in the test bench. We need to verify the log, and also we need to verify the waveforms. But in the methodology, the basics are like this. We will be having a constraint random stimulus. Constraint random stimulus means here we need to understand the random stimulus first, and then what are constraints. Random stimulus is generating the random values for the inputs. Suppose if you have a data line, the data we are not supposed to manually give it as 0, 0, 0, 1 like that. Randomly it will generate. That is random stimulus. Constraint random stimulus in the sense, if we want to particularly any value we need to generate, or any condition there is in our test plan for the randomization, we can put a constraint. That is called as constraint random stimulus. This random stimulus is critical for exercising the complex designs, and then we need to have a functional coverage model. When we are using a random stimulus, only that random values may cover some of the portion of the code. So functional coverage gives us what and all the other random values we need to generate for the verification of complete DUT. And then we will be having a layered test bench using transactors, where the layered test bench helps us in controlling the complexity by breaking them into a small pieces, we can say. That is layer wise test bench. And transactors, they will provide the useful pattern for building these pieces. And then common test bench for all the tests we can maintain. We will be not changing the test bench. We will be only changing the test pattern or the test values, we can say. So there are test cases we will be changing, and the test bench will be remain same. And then the last one is test case specific code kept separate from the test bench. So suppose if you have a 10 test cases, all the test cases are going to be kept separate apart from the test bench. Whenever we are going to run that, we will be taken into the test bench environment, we can say. So these are all the methodologies we need to follow, while it will reduce the time consuming by the testing. In the direct testing, it is taking this much time. You can see if you use a random test, constraint random stimulus and these concepts, the time will be reduced greatly. This dotted line indicating a random test and directed test is one after the other, it will be taking much time. So, but initially you can see to start the test, we have a set of plan to be executed before the starting. That's why direct test started early but completing late. The random test started late but completing early. So random test initially it may take time and we will be achieving the result 100% coverage of the DUT very soon, we can say. Then we need to understand what is constraint random stimulus. As I said, constraint random stimulus means we need to understand the random stimulus first. Random stimulus is giving the random values to the design and by generating the random values in our test bench. Constraints in the sense putting the constraint, putting a condition for the random generator. The simulator is going to generate the random stimulus, but we can have a control on that using constraints. And here in the figure you can see the first one is direct test coverage. So we will be having these are the different blocks, each and every blocks, and a smiley indicating the test is successful and this indicating there is a bug, right? And each and every block of code or the blocks are going to be taken and verified. Here you can see the boxes indicating much area is covered and there might be a chance of going into the new area also. In such cases, if that new area is not comes under our constraint, we need to write the more constraint for the randomization and we can avoid those areas also. So that way, that is where the constraints are going to be helpful. Means we are putting a condition for the random value generator. If you give a random value and your limit is like only 4 values, if it is generating 10 values, all other 6 values are out of the scope. That's why we need to have a constraint that it should be limited to 4 values like that. Then we'll be having a coverage convergence diagram. So if we use a constraints, you can see here at the left we'll be having add constraints. Once we add the constraints, a condition, the constraints in the sense simply if I say if you are verifying a memory write and read operations, there are two control signals. One is write enable, another one is read enable. Assume like the specification says write and read should not happen at a time. In such case, we need to put a constraint for the random generator that if you generate the random value for write enable, read enable, please take care of keeping those two complementary to each other. Means when the write is happening with write enable is equal to 1, read enable should be 0. It should not randomly generate read and write is equal to 1. So such random conditions we can add over here as a constraint. Then it becomes constraint random test. Then many runs we can do with different seeds. Seeds in the sense if we give a randomization in the test bench with seed is equal to 1, it will generate a certain pattern. If you give seed is equal to true, seed becomes 2 means the pattern of random generator values will be changed. That means the seed. So if the seed value changes, the values what the random generator is going to generate changes. That's why many runs we can perform on the same test with different seeds. Then it will cover the much functional area. So functional coverage will be achieved. Then identifying the holes or the bugs. And then minimal code modifications can be done. And again, we'll be adding the constraints and this loop continues. And in the directed cases, what happens? We'll be having a directed test case. We'll be checking the coverage. Again, we'll be facing a bug. Again, minimal code changes we need to do. Again, we need to give the manually directed values. This loop continues and it takes much time. But if you have a constraint random values and also the seeds we are changing means the values which we generated are going to be changed and given as new values and we'll be achieving the functional coverage very soon, we can say. So this is about the coverage and the advantage when we are going with the constraint random stimulus other than direct values, right? And then we need to understand why we need to randomize the things. Why can't we give it manually as we do in the Verilog test bench, right? So then let us understand what should you randomize. What should you randomize means which are all the things you need to put it under randomization, which all it will cover, which it will not cover, and how the randomization we need to control. So the randomizing stimulus can be generated by using simple $random function. Even in System Verilog, you can use a randomize function directly we can call and randomize the things. But the problem is that choosing this method gives us very low finding of bugs. It means the primary types of bugs in the sense we'll be finding in the random data as data path errors. Data path in the sense the functionality errors and some peripherals are with bit level mistakes. Those things we can identify using this randomized values. But we need to find the bugs in the control logic also. Control logic in the sense, as I said, write and read should not happen. If it is happen, what happens? Those kind of things we need to identify. And also there are different control signals will be there in our complex designs. And also these things we need to check means we need to think of the device configuration and also the environment configuration and what the input data I need to give and which are all the, suppose if you are testing any protocol exceptions are there any, we need to consider those, or we can treat that as a bug or not, and errors and the violations whether they are legible or we can skip those, and how the delays will be in the design. So these things we need to consider it carefully, then only we will be come to know that what should you randomize and what we should not randomize. So these are the very important things in the verification we need to understand. So let us see these things in the next video, second part of this lecture. So we will be understanding more about the verification aspects in that. The test book which you are supposed to refer here is the System Verilog for Verification, a guide to learning the Testbench language features. That is the second one. And also there are some videos related to the advanced verification concepts in the Explore Electronics Plus channel. You can visit that and learn more about the industry related verification aspects. Thank you.